Hello there and welcome back. Tonight we're going to drift through one of the most fundamental forces in the universe, the gentle pull that holds everything together. Gravity. It's always there, quiet and constant, keeping your feet on the ground and the moon circling overhead. But beneath that familiar tug lies a universe of wonder. Tonight, we'll explore the most calming and beautiful truths about gravity. Facts that reveal how this invisible force shapes everything from falling leaves to distant galaxies. Some of these ideas will feel familiar, like old friends. Others might surprise you with their strangeness. But each one invites you to slow down, to breathe, and to marvel at the elegant simplicity woven into the fabric of reality. If you enjoy drifting off to the mysteries of the universe, feel free to like and subscribe. But for now, just settle in. Let your shoulders drop, your breathing deepen, and allow these gentle truths about gravity to carry you softly toward sleep. Let's begin. Gravity is the weakest force in nature. Of all the forces that govern the universe, gravity is by far the gentlest. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth when it lifts a paperclip. The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate with vastly more power at small scales. Yet gravity never stops. It reaches across infinite distances, patient and persistent. While other forces fade or cancel out, gravity simply accumulates. Every atom, every particle, every wisp of matter contributes its small pull. Alone, these tugs are almost nothing, but together, over vast distances and enormous masses, they become the architects of planets, stars, and galaxies. The weakness of gravity is what makes the universe possible. If it were stronger, stars would collapse too quickly. Planets might never form. Life as we know it could never emerge. In its gentleness lies its power. Like water shaping stone, gravity works slowly but shapes everything. Everything falls at the same speed in a vacuum. Drop a feather and a hammer on Earth, and the feather floats down while the hammer plunges. But this difference comes from air resistance, not gravity. In the absence of air, both fall at exactly the same rate. This truth was demonstrated on the moon by astronaut David Scott during the Apollo 15 mission. He held a hammer in one hand and a feather in the other, then released them simultaneously. Both touched the lunar surface at the same instant. No air to interfere, just gravity doing its work. This principle was first understood by Galileo centuries ago, though the story of him dropping weights from the Leaning Tower of Pisa may be legend. What matters is the insight. Gravity pulls on all objects equally, regardless of their mass. A pebble and a planet accelerate toward each other at rates determined only by their masses and the distance between them. In the perfect stillness of space, a grain of sand and a mountain would fall together side by side toward any massive body. It's a reminder that gravity treats all matter with the same gentle insistence. Gravity is not a force, but a curve in space. For centuries, people imagined gravity as an invisible rope pulling objects together. Then Einstein offered a different vision. He showed that massive objects don't pull on other objects. Instead, they bend the fabric of space and time around them. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it curves toward the bowling ball, not because of a pulling force, but because it's following the curved surface. This is how gravity works. The sun doesn't reach out and grab Earth. Instead, the sun's mass warps space-time and Earth moves along the straightest path it can through that curved landscape. What we call orbits are simply objects following the natural contours of bent space. This insight changed everything. Gravity became geometry. The universe itself became a flexible, dynamic structure, shaped by the matter and energy within it. When you fall, you're not being pulled downward. You're simply moving along the curve that Earth's mass has created in the space-time around you. Time moves slower in stronger gravity. One of the strangest truths about gravity is that it affects not just space but time itself. Clocks tick more slowly when they're closer to a massive object. This isn't a malfunction or a trick. Time genuinely passes at different rates depending on how deep you are in a gravitational well. A clock on the ground runs slightly slower than one on top of a mountain. The difference is tiny, just fractions of a second over a lifetime, but it's real and measurable. Satellites in orbit must account for this effect. The GPS system in your phone relies on clocks aboard satellites, and those clocks tick faster than the ones on Earth's surface. If engineers didn't correct for this time dilation, your navigation would drift off course by miles within days. Near a black hole, where gravity is immense, time slows dramatically. An observer far away would see someone falling toward a black hole, moving slower and slower, their clock nearly stopping as they approach the event horizon. For the person falling, time feels normal, but outside, the universe ages faster. Gravity doesn't just shape where things go, it shapes when things happen. Gravity holds galaxies together. Look up at the night sky and you're seeing the work of gravity written in light. Every star, every swirling galaxy, every cluster of galaxies exists because gravity drew matter together over billions of years. In the beginning, the universe was nearly smooth, just hydrogen and helium spread almost evenly through space. But almost isn't perfectly. Tiny fluctuations, regions with just slightly more matter than others, created gentle gravitational pulls. Over time, these pulls drew in more matter. The rich got richer. Dense regions grew denser. Eventually, these growing clumps of matter collapsed inward, forming the first stars. Stars grouped into galaxies. Galaxies gathered into clusters. All of it held together by gravity's patient accumulation. Even now, galaxies are moving through space, drawn toward the largest concentrations of mass. Our own Milky Way is drifting toward a region called the Great Attractor, pulled by the combined gravity of countless galaxies. Gravity is the thread that weaves the cosmic web, connecting everything across unimaginable distances. Without it, the universe would be a cold, empty void with matter scattered and alone. You are constantly falling toward the center of the Earth. Right now, as you rest, you're falling. Gravity is pulling you downward, accelerating you toward the planet's core. The only reason you don't plunge through the floor is that the ground pushes back with equal force. This upward push is what you feel as weight. If the ground were suddenly removed, you'd fall freely, accelerating smoothly downward. Astronauts aboard the space station experience this constantly. They're falling toward Earth just like you, but they're also moving forward so fast that they keep missing the planet. Their path curves downward, but Earth's surface curves away beneath them at the same rate. This is what orbit is. Continuous falling without ever hitting the ground. When you jump, you experience a brief moment of free fall. For that instant, you're weightless, falling through the air until the ground rushes up to meet you. Roller coasters and drop towers create the same sensation by letting you fall freely for a few seconds. Gravity never stops pulling. It's always there, a constant companion, drawing you gently downward. The ground simply holds you up, resisting that pull, and the tension between the two is what you feel as the solidity of the world beneath you. Gravity travels at the speed of light. If the sun suddenly vanished, Earth wouldn't immediately fly off into space. For about 8 minutes, we'd continue orbiting the spot where the sun used to be. This is because gravitational effects travel at the speed of light, just like light itself. Changes in gravity ripple outward through space-time at this cosmic speed limit. When two black holes spiral toward each other and merge, they create waves in the fabric of space itself. These gravitational waves spread outward in all directions, traveling at the speed of light. They stretch and squeeze space as they pass, and scientists can detect these tiny distortions using incredibly sensitive instruments. The first gravitational wave detection came in 2015, confirming what Einstein predicted a century earlier. Since then, dozens more have been observed, each one a message from violent cosmic events billions of light years away. Gravity isn't instant. It takes time to cross distances. But at the speed of light, it's fast enough that for most everyday purposes, it feels immediate. The delay only matters across cosmic scales, where light itself takes minutes, years, or even billions of years to travel. Black holes are places where gravity becomes infinite. At the heart of a black hole lies a point called a singularity. Here, matter is crushed to infinite density, and gravity becomes so strong that the fabric of space-time itself breaks down. Our equations fail. The rules we know stop working. This is the ultimate expression of gravity, a place where the force becomes so overwhelming that nothing, not even light, can escape. The boundary around a black hole is called the event horizon. Cross this line and there's no turning back. Every path, every direction leads inward toward the singularity. Time and space switch roles. Moving forward in time becomes the same as moving toward the center. For someone watching from a safe distance, an object falling toward a black hole would appear to slow down, freeze, and fade as light struggles to escape the intense gravity. But for the one falling, time continues normally until the very end. Black holes are gravity's final statement, a reminder that this gentle force, given enough concentration, can become the most powerful thing in the universe. They are mysteries wrapped in darkness, places where our understanding reaches its limit and the universe keeps its deepest secrets. Gravity makes time feel different on mountains and in valleys. If you've ever stood on a mountain peak, time was moving just slightly faster for you than for someone in a valley below. The difference is minuscule, but it's there. Gravity is weaker at higher altitudes because you're farther from Earth's center. Weaker gravity means time flows more quickly. Climb a mountain and your clock ticks faster. Descend into a mine shaft and it slows down. This effect has been measured with atomic clocks, devices so precise they can detect differences of less than a billionth of a second. Scientists have placed identical clocks at different elevations and watched as the one at higher altitude gradually pulls ahead. Over a human lifetime, someone living at high altitude would age a tiny fraction of a second more than someone at sea level. You'd never notice it, but the universe keeps precise accounts. This warping of time by gravity is constant and everywhere. Every hill, every building, every change in elevation creates a slight shift in how quickly time passes. We live in a landscape where time itself has contours, flowing at different rates depending on where we stand. The moon's gravity creates the tides. Twice each day, the ocean rises and falls along coastlines around the world. This rhythm is driven by the moon's gravity pulling on Earth's water. The side of Earth facing the moon feels a stronger pull than the center of the planet, and the far side feels an even weaker pull. This difference in gravitational strength stretches Earth slightly, creating two bulges of water. One bulge points toward the moon and the other points away. As Earth rotates beneath these bulges, coastlines move through them, experiencing high tide twice a day. The sun also contributes to tides, though its effect is smaller despite its much greater mass. When the sun and moon align during new and full moons, their gravitational pulls combine, creating especially high and low tides called spring tides. When they're at right angles during quarter moons, their effects partially cancel out, producing smaller tides called neap tides. The tides are a visible reminder that gravity reaches across space. The moon, hanging silently above, stirs the oceans below. This connection has shaped life on Earth for billions of years, creating tidal zones where creatures adapt to the constant rhythm of rising and falling water. Gravity can bend light. Light has no mass, yet gravity affects it. This seems impossible at first. How can a force that pulls on matter influence something weightless? The answer lies in Einstein's insight. Gravity doesn't pull on light directly. Instead, it curves the space through which light travels. A beam of light always moves in a straight line, but if space itself is curved, that straight path bends. This effect is called gravitational lensing. When light from a distant star passes near a massive object like a galaxy or a black hole, the light's path curves. From our perspective, the star appears in a different position than it actually is. Sometimes the light bends around both sides of the massive object, creating multiple images of the same star. In extreme cases, the light forms a perfect ring called an Einstein ring. This bending of light was one of the first confirmations of Einstein's theory of general relativity. During a solar eclipse in 1919, astronomers observed stars near the sun and found their position shifted exactly as Einstein predicted. Gravity shapes not just the paths of planets and comets, but the very light by which we see the universe. You weigh less at the equator than at the poles. Earth is not a perfect sphere. It bulges slightly at the equator due to its rotation. This means that standing at the equator places you farther from Earth's center than standing at the poles. Since gravity weakens with distance, you weigh slightly less at the equator. The difference is small, about 0.5%, but it's measurable. A person weighing 200 pounds at the North Pole would weigh about 199 pounds at the equator. Part of this difference also comes from Earth's rotation. At the equator, you're moving faster as the planet spins, and this motion creates a centrifugal effect that partially counteracts gravity's pull. At the poles, there's no such motion, so gravity's full strength is felt. This variation means that gravity isn't quite the same everywhere on Earth. Mountains, valleys, and dense rock formations all create local variations in gravitational strength. Scientists map these subtle differences to study Earth's interior, tracking how mass is distributed beneath the surface. Gravity is not uniform. It shifts and changes depending on where you are, a gentle reminder that even the ground beneath you is more complex than it seems. Gravity brought the planets into existence. Billions of years ago, the solar system was a swirling disk of gas and dust surrounding the young sun. Within this disk, tiny particles collided and stuck together, forming larger and larger clumps. Gravity drew these clumps toward each other, building up rocks, then boulders, then mountains of material. Over millions of years, these growing bodies swept up everything in their orbital paths. The largest ones became planets. Their gravity pulled them into spheres, the most stable shape under the influence of their own weight. Smaller bodies became moons, asteroids, and comets. The process was chaotic, with countless collisions and near misses. Planets migrated inward and outward, their orbits shifting as they interacted gravitationally. Some objects were flung into the outer reaches of the solar system. Others plunged into the sun. What we see today is the result of billions of years of gravitational sorting, a system that has settled into a relatively stable configuration. Gravity is both creator and organizer. It gathered the raw materials of the solar system and arranged them into the elegant structure we inhabit. Every planet, every moon, every ring and asteroid belt exists because gravity pulled matter together and held it in place. Gravity is why stars shine. Deep within a star, gravity squeezes matter inward with tremendous force. The core becomes so hot and dense that hydrogen atoms begin to fuse together, forming helium and releasing vast amounts of energy. This energy pushes outward, creating pressure that balances gravity's inward pull. The star reaches equilibrium, a delicate balance between collapse and explosion. For billions of years, this balance holds. Gravity wants to crush the star into a single point. Nuclear fusion wants to blow it apart. The two forces wrestle constantly, and the result is a steady outpouring of light and heat. Every ray of sunlight that warms your face is the product of this ancient struggle happening deep inside the sun. Without gravity, stars would never form. The clouds of gas floating through space would remain diffuse and cold. With gravity, these clouds collapse, heat up, and ignite. The universe fills with light. When a star exhausts its fuel, gravity finally wins. The core collapses, sometimes gently for Ming, a white dwarf, sometimes violently creating a supernova. The strongest gravity of all forms black holes, but even in death, stars give back. The heavy elements forged in their cores scatter into space, seeding new clouds that will one day form new stars and planets. Gravity drives this cycle: birth, life, death, and rebirth, all orchestrated by the gentlest force. Falling feels like floating. When you fall freely with nothing to support you, something strange happens. The sensation of weight vanishes. Your stomach lifts. You feel suspended, almost as if you're floating in water. This is because weight isn't gravity itself. Weight is the ground pushing up against gravity's pull. Remove the ground and the sensation disappears. Astronauts in orbit experience this constantly. They're falling around Earth, and because everything around them is falling at the same rate, they feel no weight at all. Objects hang motionless in the air. Water forms perfect spheres. Everything drifts as if suspended in an invisible fluid. This is the natural state of free fall. It's only when something interrupts your fall that weight returns. Parachutes, airplane floors, trampolines, all create the sensation of weight by pushing against your body's downward motion. The feeling of heaviness isn't gravity pulling you down. It's the resistance pushing you up. Gravity itself is silent and smooth. Falling is the most natural motion in the universe. Every orbit is a fall that never ends. Every raindrop traces the same ancient path. When you let go, when you allow yourself to fall, you're simply following the curve that mass has written into space. And for a moment, you're weightless. Gravity shaped your body. Every living thing on Earth evolved under gravity's constant presence. Your bones are strong because they need to support your weight against this downward pull. Your heart pumps blood upward, fighting gravity with every beat. Your inner ear contains tiny crystals that settle under gravity's influence, telling your brain which way is down. Without gravity, these systems would be unnecessary. In space, astronauts' bones begin to weaken. Their hearts don't need to work as hard. Fluids shift toward their heads, making their faces puffy. After months in orbit, they must relearn how to walk when they return to Earth. Gravity has sculpted not just mountains and planets, but life itself. Trees grow upward, their trunks strengthen to resist the downward pull. Birds' wings are shaped to generate lift against gravity. Fish feel its pull too, though water's buoyancy makes it gentler. Even single cells respond to gravity, organizing their internal structures in relation to up and down. You are a creature of gravity. Your posture, your gait, the way you reach and balance, all of it emerged over millions of years in response to this constant force. When you stand, you're defying gravity. When you lie down, you're surrendering to it. The gentle pressure you feel against the bed, the way your body settles and relaxes, that's gravity welcoming you home. Gravity has no opposite. Push and pull, positive and negative, north and south. Most forces in nature have opposites that can cancel each other out, but gravity is different. It only attracts. There is no anti-gravity, no way to create a gravitational repulsion. Every piece of matter pulls on every other piece, always drawing them together, never pushing apart. This one-way nature makes gravity unique among the fundamental forces. Electromagnetism can attract or repel depending on charge. The strong nuclear force binds particles together while the weak force governs decay. But gravity simply accumulates. Add more mass and the pull grows stronger. There's no way to shield yourself from it. No gravitational insulator. You can't hide from gravity. It reaches through walls, through planets, through empty space. The only way to escape a gravitational pull is to move fast enough that you're constantly falling around it rather than into it. This absence of opposition gives gravity its inexorable quality. It's patient, persistent, always present. While other forces flicker and change, gravity endures. It builds over time, gathering matter, shaping structure, creating order from chaos. The universe expands, but gravity works to pull it back together. These two tendencies, expansion and gravitational attraction, define the cosmos at its largest scale. Your weight changes throughout the day. As Earth rotates, your distance from the sun changes slightly. When the sun is overhead, its gravity adds to Earth's, making you fractionally heavier. At night, when the sun is on the opposite side of the planet, its pull partially counteracts Earth's gravity, making you slightly lighter. The difference is incredibly small, far too tiny to feel or measure with an ordinary scale. But it's there, a reminder that multiple gravitational fields overlap and combine. The moon's position also matters. When it's directly overhead or underfoot, its gravity creates a small change in your weight. Even nearby mountains exert a measurable gravitational pull, though you'd need extremely sensitive instruments to detect it. These variations are part of living on a planet that's not alone in space. We're part of a gravitational dance involving the sun, moon, planets, and even distant stars. Each body pulls on you, combining their effects in complex ways. You're not just standing on Earth, you're being gently tugged by the entire solar system. The ground beneath you is the sum of countless forces, all balanced in a way that feels solid and unchanging, but is actually dynamic and alive with subtle motion. Gravity creates waves when massive objects collide. When two black holes spiral toward each other, they stir space-time like spoons stirring honey. Ripples spread outward in all directions, carrying energy away from the collision. These gravitational waves travel at the speed of light, stretching and squeezing space as they pass. The effect is tiny. When a gravitational wave passes through Earth, it might change the distance between 2 points by less than the width of an atomic nucleus. Yet scientists can measure this. They've built detectors with laser beams traveling miles back and forth, so sensitive they can detect these minute distortions. Each detection is a triumph of precision and patience. The waves detected so far have come from black hole mergers and neutron star collisions billions of light years away. These events release more energy in a fraction of a second than the sun will produce in its entire lifetime. That energy ripples through the universe, carrying information about what happened. Gravitational waves let us observe events that produce no light, no radiation, nothing but pure distortions in space-time itself. They're a new way of seeing the universe, listening to gravity's voice across cosmic distances. Each wave is a message written in the language of curved space, telling stories of violence and collision from the depths of time. Gravity slows down near massive objects. Imagine two identical clocks, one on Earth's surface and one aboard a satellite in high orbit. The clock on the ground ticks more slowly because it's deeper in Earth's gravitational well. This isn't a defect or measurement error. Time itself passes at different rates depending on gravitational strength. This time dilation is a fundamental feature of reality. It means that if you could watch someone near a black hole from a safe distance, you'd see them moving in slow motion. Their voice would deepen, their gestures would stretch out. From their perspective, everything feels normal. But to you, time around them has slowed to a crawl. This effect, though usually tiny, has practical consequences. GPS satellites orbit high above Earth where gravity is weaker and time runs faster. If we didn't account for this speed up, navigation systems would drift out of alignment within hours. The corrections needed are small but essential. Time and gravity are woven together so tightly that you cannot separate them. Where gravity is strong, time slows. Where gravity is weak, time quickens. This means the universe doesn't have a single universal clock. Time flows at different rates in different places, creating a landscape where past and future are not absolute, but depend on where you stand and how fast you're moving. Gravity pulls galaxies into vast cosmic structures. Zoom out far enough and the universe reveals a pattern. Galaxies aren't scattered randomly through space. They gather into clusters, and clusters join into superclusters, forming vast filaments and walls of matter separated by enormous voids. This cosmic web is gravity's largest creation. In the early universe, matter was spread almost evenly, but tiny variations in density, quantum fluctuations from the first moments after the Big Bang, gave gravity something to work with. Regions slightly denser than average pulled in nearby matter. Over billions of years, these small differences grew. Gravity amplified them, drawing matter into denser and denser clumps. The result is a universe that looks like foam or a sponge, with matter concentrated along thin filaments and vast empty spaces in between. Our own galaxy is part of the local group, which is part of the Virgo supercluster, which is part of an even larger structure called Laniakea. All of this structure emerged from gravity acting on the raw material of the cosmos. These vast filaments contain trillions of galaxies, each one a city of stars, all held in place by gravity's gentle but persistent pull. The cosmic web is still evolving. Galaxies are still moving, still clustering, drawn by the combined gravity of all the matter around them. Gravity makes orbits possible. An orbit is a special kind of falling. You're moving forward so fast that as you fall toward a planet or star, the ground curves away beneath you at the same rate. You never get closer and you never get farther away. You simply fall around and around in a graceful loop. This balance between forward motion and downward pull creates stability. The moon orbits Earth, Earth orbits the sun orbits the center of the Milky Way. Galaxies orbit within their clusters. At every scale, gravity organizes matter into rotating systems. These orbits can last for billions of years, unchanged and predictable. Ancient astronomers noticed this regularity and used it to track time, predict eclipses, and navigate by the stars. Orbits aren't perfect circles. Most are ellipses, stretched ovals where the orbiting object moves faster when closer to the massive body and slower when farther away. This variation creates seasons on Earth as our distance from the sun changes throughout the year. Comets follow extremely elongated orbits, spending most of their time in the cold outer reaches of the solar system before plunging briefly toward the sun's warmth. Every orbit is a balance, a dance between motion and gravity. Change the speed and the orbit changes. Move too slowly and you spiral inward. Move too quickly and you escape into space. But at just the right speed, you can circle forever, held by gravity's invisible hand. Gravity determines the shape of planets. When enough matter gathers in one place, gravity pulls it inward from all directions equally. This creates a sphere, the only shape where every point on the surface is the same distance from the center. Small asteroids can be lumpy and irregular because their gravity is too weak to overcome the strength of rock. But once an object grows large enough, gravity wins. It pulls the highest peaks down and fills the lowest valleys until the surface smooths into a round form. Earth is nearly spherical, though not perfectly. The planet bulges slightly at the equator because of its rotation. Mountains rise and valleys sink, but these features are tiny compared to Earth's overall size. If you could shrink Earth to the size of a billiard ball, it would feel smoother than the polished surface. The wrinkles we see as vast mountain ranges are barely noticeable at planetary scale. Other worlds show the same pattern. Mars, Venus, Jupiter, and Saturn are all spheres, shaped by their own gravity. Even moons follow this rule once they reach sufficient size. Smaller moons remain irregular, potato-shaped rocks tumbling through space. But larger ones are round, their surfaces pulled smooth by the relentless inward tug of their own mass. The sphere is gravity's signature, a shape that appears wherever matter gathers in sufficient quantity. It's a reminder that beneath all the complexity of geology and weather, gravity works to create order and symmetry. Gravity moves at a specific speed. Changes in gravity don't happen instantly. They propagate through space at exactly the speed of light, about 186,000 miles per second. This means gravitational effects take time to travel across distances. If a massive star suddenly appeared a light year away, we wouldn't feel its gravitational pull for a full year. The distortion in space-time would spread outward like ripples on a pond, moving at light speed until it reached us. This speed limit applies to all changes in gravitational fields. When planets orbit, they create moving ripples in space-time that propagate outward. These ripples are usually far too weak to detect, but when something truly massive moves, the waves become noticeable. Black holes merging, neutron stars colliding. These catastrophic events send powerful gravitational waves racing across the universe. The fact that gravity travels at light speed connects it to the fundamental structure of space-time itself. Light, gravity, and the flow of cause and effect all share this cosmic speed limit. Nothing can travel faster. No information, no force, no influence can exceed this boundary. It's woven into the fabric of reality, a rule that governs everything from the smallest particles to the largest structures in the cosmos. When you move your hand, the tiny gravitational field around it changes, and that change spreads outward at light speed, though far too small for anyone to measure. Every motion creates ripples. Every shift in mass sends information flowing through space. The universe is alive with these signals, invisible messages written in the language of curved space-time. You are made of star material held together by gravity. Every atom in your body, except hydrogen, was forged inside a star. Carbon, oxygen, nitrogen, calcium, iron, all of them were created by nuclear fusion in stellar cores or during supernova explosions. When those ancient stars died, they scattered their enriched material into space. Gravity gathered those atoms into new clouds. Those clouds collapsed into new stars and planets. Earth formed from this recycled stardust, and eventually so did you. The iron in your blood was made in a dying star billions of years ago. The calcium in your bones was scattered across space by a supernova's shockwave. The oxygen you breathe came from countless stellar furnaces burning over cosmic time. Gravity brought all these elements together, first into a planet, then into the complex chemistry that leads to life. Without gravity, those atoms would still be drifting separately through the void, never meeting, never combining into anything interesting. You are gravity's creation in the most literal sense. Not just your body's structure, shaped to stand upright under its pull, but the very atoms you're made of were gathered and organized by gravitational collapse. Every breath, every heartbeat, every thought occurs in matter that gravity assembled from the remnants of dead stars. When you look up at the night sky, you're seeing your own distant past, the forges where your substance was born, and the force that brought it all together still holds you now, gently pressing you into the bed, reminding you that you belong to this universe and it belongs to you. Gravity creates the conditions for life. Without gravity, the universe would be a thin, cold soup of particles, spread evenly through space with no structure, no stars, no planets, no possibility of complexity. Gravity is what allows interesting things to happen. It gathers matter into dense regions where temperatures rise high enough for nuclear fusion. Stars ignite, creating light and heat. Planets form in the debris around those stars, some at just the right distance where water can exist as a liquid. Earth's gravity holds the atmosphere close to the surface. Without it, air molecules would drift away into space, leaving the planet lifeless and barren like the moon. The atmosphere traps heat, cycles water, and shields the surface from harmful radiation. All of this depends on gravity keeping those gases bound to the planet. The right amount of gravity is essential. Too much, and the atmosphere becomes thick and crushing. Too little, and it escapes entirely. Gravity also drives geological activity. The pressure deep within Earth, created by the weight of all the rock above, keeps the interior hot and fluid. This allows plate tectonics, the slow churning of Earth's crust that recycles nutrients, builds mountains, and creates diverse environments. Volcanic activity releases gases that replenish the atmosphere. All of this motion, all this dynamic geology happens because gravity compresses the planet's interior. Even the moon plays a role. Its gravity creates tides that mix the oceans and may have helped life transition from sea to land billions of years ago. The rhythmic rise and fall of water created tidal pools, unique environments where early organisms could adapt to both wet and dry conditions. Gravity didn't create life directly, but it built the stage where life could emerge and flourish. It's the invisible architect of habitability. Gravity bends the path of light around massive objects. When light from a distant galaxy passes near a closer, more massive galaxy, its path curves. The closer galaxy acts like a lens, bending the light and sometimes creating multiple images of the same distant object. These gravitational lenses let astronomers see galaxies that would otherwise be too far and too faint to detect. The massive galaxy magnifies the light from behind it, effectively creating a natural telescope in space. Sometimes the alignment is perfect and the distant galaxy appears as a ring of light around the closer one. This Einstein ring is a complete circle of distorted, magnified light, a cosmic alignment that reveals the geometry of curved spacetime. More often, the images are partial arcs or multiple distorted copies scattered around the lensing galaxy. By studying these patterns, scientists can map the distribution of mass in the foreground galaxy, including dark matter that emits no light but reveals itself through gravitational effects. Gravitational lensing has become a powerful tool for exploring the universe. It allows us to see farther than our telescopes could reach alone. It reveals the presence of invisible matter. It even lets us measure the expansion of the universe by comparing the brightness of distant objects seen through different lensing configurations. Light, though weightless, still responds to gravity's influence. Its path through space follows the curves that mass creates, bending and twisting according to the distribution of matter along the way. Every photon that reaches your eye has traveled a path shaped by the gravity of everything it passed, a journey through curved space written in the light itself. Gravity causes objects to spiral together over time. Two stars orbiting each other don't maintain the same distance forever. As they circle, they create ripples in space-time, gravitational waves that carry energy away from the system. This loss of energy causes the orbit to decay. Slowly, over millions or billions of years, the stars spiral closer together. Eventually, they may merge, creating a larger star or, if they're dense enough, a black hole. The same process happens with black holes. When two black holes orbit each other, they radiate gravitational waves. The orbit shrinks, the rotation speeds up, and the waves grow stronger. In the final moments before merger, the black holes spiral together at a significant fraction of light speed, releasing more energy in gravitational waves than all the stars in the observable universe emit as light. Then they collide, merging into a single, larger black hole. The space-time around them rings like a bell, settling into a new, stable configuration. This in-spiral happens everywhere in the universe. Binary stars slowly draw together. Planets very close to their stars gradually fall inward. Even Earth's orbit is decaying, though so slowly it will take trillions of years to notice. The process is a consequence of gravity's ability to create waves in space-time. Every orbiting system leaks energy through these waves, and over cosmic timescales, that loss reshapes the system. Orbits that seem eternal are actually temporary, slowly winding down toward eventual collision or merger. Gravity ensures that nothing lasts forever. Even the most stable configurations eventually change. Gravity makes escape difficult, but not impossible. To leave Earth permanently, an object must reach escape velocity, about 7 miles per second. At this speed, the object's kinetic energy equals the gravitational potential energy binding it to the planet. Move faster than this, and you can coast away into space without ever falling back. Move slower, and gravity will eventually pull you down. This threshold exists for every massive object. The moon's escape velocity is much lower because it's less massive. The sun's is much higher. A black hole's escape velocity exceeds the speed of light, which is why nothing can leave once it crosses the event horizon. Escape velocity depends only on mass and distance. The more massive the object and the closer you are to it, the faster you must move to break free. Rockets don't usually reach escape velocity directly. Instead, they accelerate gradually, climbing out of the gravitational well in stages. Once in orbit, a spacecraft is still bound to Earth, but a relatively small additional boost can push it past escape velocity, sending it toward other planets or out of the solar system entirely. Several probes have already done this, carrying messages from humanity into interstellar space. They're no longer bound to the sun, they're falling through the galaxy, following the gentle gravitational currents between stars. Escape is possible, but it requires energy and speed. Gravity doesn't trap you permanently, but it makes leaving a challenge. The deeper you are in a gravitational well, the harder it is to climb out. Yet with enough velocity, any bond can be broken. The universe allows freedom of movement, but gravity ensures it must be earned. Gravity keeps rings around planets. Saturn's rings are made of countless chunks of ice and rock, each one orbiting the planet independently. They range in size from tiny grains to house-sized boulders, all held in place by Saturn's gravity. The rings are thin, sometimes only tens of meters thick, but they stretch for hundreds of thousands of kilometers. They formed either from a moon that wandered too close and was torn apart by tidal forces, or from material that never coalesced into a moon in the first place. Each particle in the rings follows its own orbit, moving at a speed determined by its distance from Saturn. Closer particles orbit faster, farther ones move more slowly. This creates a smooth, flowing structure that looks solid from a distance but is actually a swarm of individual objects, each responding to gravity's pull. Gaps appear where Moon's gravity clears out material, creating divisions like lanes in a cosmic highway. Other planets have rings too, though none as spectacular as Saturn's. Jupiter, Uranus, and Neptune all have faint ring systems made of darker material. Even some asteroids have been found with tiny rings. The common thread is gravity. Anytime debris orbits a massive body within a certain distance, It can form a ring instead of clumping into a moon. The tidal forces are too strong for the material to stick together, so it remains spread out in a flat disk. Rings are temporary on cosmic timescales. The particles slowly spiral inward or get ejected outward. Saturn's rings may be only a few 100 million years old, young compared to the planet itself. Eventually they'll fade, raining down onto Saturn's atmosphere or drifting away into space. For now, they remain a beautiful reminder of gravity's ability to organize matter into delicate, intricate patterns. Your weight would change on different planets. Step onto Mars, and you'd weigh about a third of what you do on Earth. Mars is smaller and less massive, so its gravity is weaker. You could jump higher, lift heavier objects, and move with an ease that would feel almost superhuman. But travel to Jupiter and you'd be crushed. Jupiter's immense mass creates gravity more than twice as strong as Earth's. Walking would be exhausting, standing would strain your bones and muscles. On the moon, gravity is only 1/6 of Earth's. Astronauts bounced across the surface in slow, graceful arcs, their weight reduced to almost nothing. Every step became a leap. Objects fell slowly, giving everything a dreamlike quality. This low gravity also means the moon can't hold an atmosphere. Gas molecules move too quickly and escape into space. Weight is simply the force of gravity pulling on your mass. Your mass stays the same wherever you go, but your weight changes depending on the gravitational field around you. On a neutron star, you'd weigh billions of times more than on Earth, though you'd be crushed instantly by the immense gravity. In deep space, far from any star or planet, you'd be weightless, floating freely with nothing to pull you down. This variation shows that weight isn't a fundamental property of matter. It's a relationship between your mass and the mass of whatever you're near. Gravity creates weight by pulling objects together, and the strength of that pull depends entirely on how much mass is involved and how far apart the objects are. In this way, your weight is a conversation between you and the planet beneath you, a measure of how strongly you're being held. Gravity explains why we have day and night. Earth spins on its axis once every 24 hours, rotating through the light of the sun and into its own shadow. This rotation was set in motion billions of years ago during the planet's formation, when countless collisions of smaller bodies imparted angular momentum. Once spinning, Earth continues rotating because there's nothing in space to stop it. The vacuum provides no friction. But gravity plays a role too. The moon's gravitational pull creates tides not just in the oceans, but in the solid Earth itself. The planet flexes slightly as the moon passes overhead, and this flexing creates friction deep within. That friction converts rotational energy into heat, gradually slowing Earth's spin. Days are getting longer, though by only a tiny fraction of a second per century. Billions of years ago, days were much shorter, perhaps only a few hours long. As the moon's gravity continues to act, Earth's rotation will keep slowing. Eventually, in the distant future, one side of Earth will always face the moon, just as one side of the moon always faces Earth. This is called tidal locking, and it's gravity's way of synchronizing rotations over immense timescales. The cycle of day and night feels eternal, but it's gradually changing. Gravity never stops working, even on timescales far longer than human civilization. The pull between Earth and Moon continues to reshape both bodies, slowing rotations, altering orbits, and binding them ever more tightly together. Day and night exist because Earth spins and gravity is slowly, patiently, changing how fast that spin occurs. Gravity holds the atmosphere in place. Earth's blanket of air, the mixture of nitrogen, oxygen, and trace gases that you breathe, stays close to the surface because gravity pulls it downward. Gas molecules move quickly, bouncing off each other in constant random motion. But gravity provides a constant downward tug that keeps them from escaping into space. The atmosphere is thickest at sea level, where the weight of all the air above compresses it. As you climb higher, the air thins. Fewer molecules occupy each cubic meter. At the top of mountains, breathing becomes difficult. In the upper atmosphere, the air is so thin it's nearly a vacuum. Smaller worlds can't hold atmospheres as easily. The moon's gravity is too weak. Any gases released by volcanic activity or delivered by comet impacts quickly escape. Mars has a thin atmosphere because its lower gravity and lack of a magnetic field allowed solar wind to strip away most of its air over billions of years. Venus, similar in size to Earth, has a thick atmosphere because its stronger gravity holds onto gases more effectively. Without gravity, Earth's atmosphere would disperse into space within days. The air you breathe, the weather patterns that bring rain, the protective ozone layer that shields you from radiation, all of it depends on gravity's steady pull. Every breath you take is possible because the planet beneath you is massive enough to hold air close. Gravity doesn't just shape rock and water, it shapes the invisible ocean of gas surrounding the planet, creating the conditions where life can flourish and where voices can carry sound from one person to another. Gravity determines how stars die. A star's fate depends almost entirely on its mass, which determines the strength of its gravity. Small stars burn slowly and gently. When their fuel runs out, they shed their outer layers and fade into white dwarfs, cooling embers that will glow faintly for trillions of years. Their gravity isn't strong enough to trigger more dramatic endings. Medium stars like the Sun swell into red giants, fusing heavier elements in their cores until they too shed their outer layers, leaving behind white dwarfs. These dying stars create beautiful planetary nebulae, glowing shells of gas expanding into space. But again, their gravity stops short of anything more violent. Massive stars face a different end. Their immense gravity compresses the core to extraordinary densities and temperatures, allowing fusion of elements all the way up to iron. But iron fusion consumes energy rather than releasing it. When the core becomes iron, fusion stops. With no outward pressure to resist gravity's inward crush, the core collapses in less than a second. The outer layers fall inward and then rebound in a supernova, an explosion so bright it can outshine an entire galaxy. What remains depends on the original mass. Stars up to about 20 times the Sun's mass leave behind neutron stars, objects so dense that a teaspoon of their material would weigh billions of tons. Even more massive stars collapse completely into black holes, where gravity becomes so strong that space-time itself tears open. The star's fate was written in its mass from the beginning. Gravity determined how it would burn, how long it would live, and how it would die. Gravity connects everything in the universe. No matter how far apart two objects are, they exert gravitational force on each other. The force may be unimaginably small across vast distances, but it's never zero. You are gravitationally connected to every star, every planet, every particle in the observable universe. They pull on you, and you pull on them. The effect is negligible for distant objects, but the principle remains. Gravity has infinite range. This universal connection means the universe is not a collection of isolated objects, but a single, interconnected whole. Every motion affects every other motion, at least infinitesimally. When a star explodes on the far side of the galaxy, its gravitational influence shifts slightly, and that shift propagates outward at the speed of light, eventually reaching here. The effect is too small to measure, but it exists. In a very real sense, you are part of the gravitational field of the entire cosmos. The curvature of space-time around you is influenced by everything that has mass, everywhere. You exist within a web of gravitational connections stretching across billions of light years. This web shaped the formation of galaxies, guided the paths of stars, and brought the matter together that eventually became you. Gravity is the thread that weaves the universe into a coherent whole. It's the reason structure exists, why matter clumps into stars and planets rather than spreading uniformly through space. It's the force that connects past to future, allowing the universe to evolve and change while maintaining continuity. In the quiet pull you feel right now, pressing you gently into rest, you're experiencing the same force that binds galaxies and bends light across cosmic voids. You are held by the universe itself, cradled in the gentle curves of space-time, connected to everything that is, was, or ever will be. Gravity created the very first structures after the Big Bang. In the beginning, the universe was almost perfectly smooth. Matter and energy spread evenly in all directions, a hot, dense fog with barely any variation. But almost smooth is not the same as perfectly smooth. Tiny fluctuations existed, regions where density varied by less than 1 part in 100,000. These quantum ripples, born in the first fractions of a second, gave gravity something to work with. As the universe expanded and cooled, gravity began pulling matter toward these slightly denser regions. Over millions of years, the differences grew. Dense areas became denser, drawing in more matter from their surroundings. Empty regions became emptier as their contents drifted away. Gravity amplified the tiny imperfections, turning whispers into echoes, echoes into voices, voices into the grand structures we see today. The first stars formed in these dense pockets perhaps 100 million years after the Big Bang. They were massive, brilliant, and short-lived, burning through their fuel in only a few million years before exploding. But their brief existence seeded the cosmos with heavier elements, and their gravity helped pull together the next generation of stars. Galaxy by galaxy, cluster by cluster, gravity built the universe's architecture from nearly nothing. Every structure you see in the night sky emerged from imperfections so small they were almost not there at all. Gravity found them, nurtured them, and turned them into worlds. Gravity makes some places in space completely still. Deep in space, there exist points called Lagrange points where gravitational forces balance perfectly. These are locations where the pull of two massive bodies, say the Earth and the Sun, combine with the centrifugal effect of orbital motion to create zones of equilibrium. Place an object at one of these points and it will stay there, neither drifting toward one body nor the other. 5 such points exist in the Earth-Sun system. 3 lie along the line connecting the two bodies, unstable positions where a small nudge will send an object drifting away. The other 2 form equilateral triangles with Earth and Sun, stable pockets where objects can remain indefinitely. Some asteroids have collected in Jupiter's Lagrange points, trapped there for billions of years. Space telescopes have been placed at Earth-Sun Lagrange points, floating in perfect balance, needing almost no fuel to maintain their positions. These still points are gravity's quiet places, locations where competing forces cancel out and motion ceases. They're reminders that even in the dynamic dance of orbits and falls, there are moments of perfect calm. In the vast emptiness between worlds, these invisible anchors hold steady, offering rare stability in a universe defined by motion. Gravity affects how quickly things age. Two twins, one staying on Earth and the other traveling at high speed through space, will age at different rates. When they reunite, the traveling twin will be younger. This is not science fiction, but a consequence of how gravity and motion affect time. The twin who traveled experienced weaker gravity and higher speeds, both of which altered the flow of time. From their perspective, everything felt normal, but measured against each other, their clocks diverged. This time, dilation means that astronauts aboard the space station age slightly more slowly than people on the ground, though the difference is tiny, only fractions of a second over months in orbit. For someone near a black hole, the effect becomes dramatic. Time slows so much that hours for them could equal years for distant observers. They wouldn't feel different, but the universe around them would age rapidly. In theory, you could travel to the future by spending time in a strong gravitational field or moving at speeds close to light. When you returned, decades or centuries might have passed for everyone else. Gravity doesn't just shape where things go. It shapes when they arrive. Every moment you experience is influenced by the gravitational field around you, ticking at a rate determined by the mass beneath your feet and the speed of your motion through space. Gravity keeps binary stars dancing together. Many stars don't travel alone through space. They orbit in pairs, bound together by mutual gravitational attraction. These binary systems are common, perhaps even more common than solitary stars. The two stars circle their shared center of mass, sometimes taking only hours to complete an orbit, sometimes requiring thousands of years. When the stars are similar in mass, they orbit a point midway between them. When one is much more massive, the smaller star traces a wide loop while the larger one barely moves. The dance can be stable for billions of years, the two stars aging together, their light mingling in the darkness. Sometimes they're so close that material flows from one to the other, creating glowing streams of gas that spiral between them. If the stars are close enough, their orbits decay over time as gravitational waves carry energy away. Eventually, they may merge, either creating a single larger star or, if they're dense enough, triggering a supernova. Until then, they remain locked in their eternal waltz, bound by gravity, moving together through the galaxy. Their partnership is written in the curves of space-time, two masses following paths determined by each other's presence. They are never alone, forever held by the invisible threads that connect them. Gravity determines whether a star becomes a neutron star or black hole. When a massive star explodes in a supernova, its core collapses. What happens next depends entirely on how much mass remains. If the core is less than about 3 times the sun's mass, gravity compresses it into a neutron star. Protons and electrons are crushed together, forming neutrons. The result is an object the size of a city but containing more mass than the sun, so dense that a single teaspoon would weigh as much as a mountain. Neutron stars have solid crusts of iron nuclei and interiors made of superfluid neutrons that flow without friction. Their gravity is immense. Standing on the surface, if you could survive, you'd weigh billions of times more than on Earth. Light itself bends sharply around them, and their magnetic fields are the strongest in the universe. But if the collapsing core exceeds 3 solar masses, gravity wins completely. Nothing can resist the inward crush. The core collapses past the neutron star stage, shrinking without limit. An event horizon forms, a boundary beyond which escape is impossible. A black hole is born. The difference between a neutron star and a black hole is simply mass. A little less, and you get a strange but observable object. A little more, and you get a tear in space-time itself. Gravity makes the choice, and the universe must live with the result. Gravity allows planets to have moons. Earth's moon is a companion, a smaller world bound to ours by gravity. It orbits at a distance of about 240,000 miles, held in place by the same force that keeps your feet on the ground. The moon's presence stabilizes Earth's rotation, preventing wild swings in axial tilt that would make the climate chaotic. It creates tides that mix the oceans and may have helped life emerge billions of years ago. Other planets have moons too. Mars has 2 tiny captured asteroids. Jupiter has nearly 80 known moons, some larger than planets, others barely a mile across. Saturn's moon Titan has a thick atmosphere and liquid lakes. Europa hides an ocean beneath its ice. Each moon tells a story of how it formed, whether condensing from the same disk that created its planet or being captured later by gravitational attraction. Moons can't orbit too closely or they'll be torn apart by tidal forces. They can't orbit too distantly or they'll drift away, stolen by the sun's gravity. There's a zone around each planet where moons can exist stably, held in balance between these extremes. Within that zone, gravity allows these smaller worlds to circle their parents, sometimes for billions of years. The moon above you tonight is ancient, formed perhaps 4.5 billion years ago, and gravity has kept it circling Earth ever since. It's a reminder that even in the vastness of space, companionship is possible, held together by invisible bonds. Gravity explains why raindrops fall at a steady speed. When a raindrop first forms high in a cloud, gravity pulls it downward. It accelerates, moving faster and faster. But as it speeds up, air resistance increases. The faster it falls, the more the air pushes back. Eventually, the upward force of air resistance equals the downward pull of gravity. At this point, acceleration stops. The drop continues falling, but at a constant speed called terminal velocity. For a typical raindrop, terminal velocity is about 20 miles per hour. Larger drops fall faster because their weight overcomes air resistance more easily. Tiny droplets fall slowly, drifting gently downward. This balance between gravity and air resistance is why rain falls in drops rather than in solid sheets, and why you can stand in a rainstorm without being injured. If drops fell with unimpeded acceleration from cloud height, they would strike the ground at hundreds of miles per hour. Every falling object reaches this balance. Skydivers spread their arms and legs to increase air resistance, slowing their descent. They can control their speed by changing their body position, using the air to counteract gravity's pull. When they open their parachutes, air resistance increases dramatically, and their terminal velocity drops to a gentle few miles per hour. Gravity still pulls, but the air pushes back just as hard, creating a slow, safe descent. The same principle governs leaves drifting from trees, seeds carried on the wind, and snow falling softly to the ground. Gravity keeps asteroids in the belt between Mars and Jupiter. Between the orbits of Mars and Jupiter lies a region filled with rocky debris, the asteroid belt. Millions of objects orbit here, ranging from tiny pebbles to bodies hundreds of miles across. They're held in place by the sun's gravity, each one following its own elliptical path. The belt isn't densely packed. Spacecraft pass through it without difficulty. The asteroids spread so far apart that collisions are rare. These objects are leftover material from the solar system's formation. They never coalesced into a planet, possibly because Jupiter's immense gravity stirred the region, preventing the rocks from settling into stable orbits long enough to stick together. Instead, they remain scattered, a ring of debris marking the boundary between the rocky inner planets and the gas giants beyond. Some asteroids occasionally drift out of the belt, nudged by collisions or gravitational interactions. These can cross Earth's orbit, becoming potential threats. Most burn up in the atmosphere as meteors. A few large ones have struck the surface, creating craters and occasionally triggering mass extinctions. Gravity governs their paths, determining whether they remain safely distant or swing inward toward the inner solar system. The asteroid belt is a reminder that planet formation isn't always successful. Sometimes gravity gathers matter into worlds, sometimes it leaves behind fragments, scattered remnants of what might have been. These rocks orbit in the darkness, bound to the sun, never quite becoming something greater, but never quite disappearing either. Gravity makes gas giants possible. Jupiter, Saturn, Uranus, and Neptune are fundamentally different from Earth. They have no solid surface. Their interiors are layers of gas and liquid compressed by gravity into states that don't exist naturally on Earth. At their cores, pressures are so immense that hydrogen behaves like a metal, conducting electricity and generating powerful magnetic fields. These planets form farther from the sun, where temperatures were cold enough for ice and gas to condense. Gravity pulled this material together, building massive worlds quickly before the young sun's heat could blow the gas away. Once they grew large enough, their gravity became strong enough to capture even more gas directly from the surrounding nebula. They swelled into giants, accumulating atmospheres thousands of miles deep. Jupiter's mass is more than twice that of all other planets combined. Its gravity dominates the outer solar system, flinging comets inward or outward, clearing gaps in the asteroid belt and capturing dozens of moons. Saturn's lower density means it would float if you could find an ocean large enough. Both planets radiate more heat than they receive from the sun, their interiors still warm from the energy of their formation billions of years ago. Without strong gravity, these giants couldn't exist. Their mass is what allows them to hold on to such thick atmospheres. On smaller worlds, gas would escape into space, but on Jupiter and Saturn, gravity compresses the atmosphere until the boundary between gas and liquid disappears. There's no surface to stand on, only layers of increasing density descending into darkness. They are worlds made almost entirely of the lightest elements, held together by gravity's patient, crushing grip. Gravity makes some orbits more stable than others. Not all orbits last forever. Some are stable, remaining unchanged for billions of years. Others are chaotic, shifting unpredictably until the orbiting object either collides with something or gets flung away. The difference comes down to gravitational influences from nearby bodies. Earth's orbit is stable. It circles the sun in a near-perfect ellipse. varying by only a few percent in distance throughout the year. This stability has persisted for billions of years and will continue for billions more. The other planets tug on Earth slightly, causing small variations, but nothing dramatic enough to destabilize the orbit. In contrast, some asteroids follow chaotic paths. Jupiter's gravity nudges them each time they pass, gradually altering their orbits in unpredictable ways. Over millions of years, these small changes accumulate. The asteroid might be flung into the inner solar system, ejected from the solar system entirely, or sent crashing into a planet. Predicting exactly what will happen becomes impossible beyond a certain timescale. Moons can have unstable orbits too, especially small ones captured by a planet's gravity rather than forming alongside it. These moons may eventually collide with their planet, break apart, or drift away. Stability requires a balance, the right distance, the right speed, and minimal interference from other gravitational sources. When that balance exists, orbits can endure almost indefinitely. When it doesn't, change is inevitable. Gravity creates tidal forces that can tear objects apart. Tidal forces arise because gravity weakens with distance. The side of an object closer to a massive body feels stronger pull than the far side. Usually this difference is small, but near extremely massive or dense objects, the gradient becomes steep. The difference in pull between near and far sides grows large enough to stretch and deform the object. The moon creates tidal forces on Earth, pulling the oceans into bulges. Earth creates tidal forces on the moon too, which long ago slowed the moon's rotation until one side permanently faces us. Both bodies survive these forces because they're solid enough and far enough apart that the stress doesn't exceed their structural strength. But move too close to a massive body and tidal forces become destructive. There's a boundary called the Roche limit. Inside this distance, tidal forces overcome the gravity holding an object together. The object stretches, deforms, and eventually tears apart. This is likely how Saturn's rings formed, a moon that wandered too close and was shredded into countless fragments. Near a black hole, tidal forces become extreme. An astronaut falling feet first would feel their feet pulled much harder than their head. The difference would stretch them like taffy in a process gruesomely called spaghettification. Long before reaching the event horizon, the tidal forces would rip them apart at the molecular level. Tidal forces are gravity's reminder that even its gentle pull can become violent under the right conditions. Gravity allows for gravitational assists in space travel. When a spacecraft approaches a planet, it can use the planet's gravity to change speed and direction without burning fuel. This maneuver, called a gravitational assist or slingshot, lets spacecraft reach distant destinations that would otherwise require impossibly large amounts of fuel. As the spacecraft approaches, it falls toward the planet, gaining speed. The planet's motion through space adds to this. If the trajectory is planned correctly, the spacecraft whips around the planet and flies away faster than it arrived, stealing a tiny bit of the planet's orbital momentum. The planet slows imperceptibly, but the spacecraft gains significant velocity. NASA's Voyager probes used multiple gravitational assists to visit Jupiter, Saturn, Uranus, and Neptune. Without these boosts, the missions would have taken decades longer or been impossible with the rockets available. The technique requires precise calculations. Arrive at the wrong angle or speed, and the spacecraft might crash into the planet or be flung off course. Gravitational assists turn planets into stepping stones, each one providing a boost toward the next destination. It's a way of borrowing energy from the solar system itself, using gravity's predictable paths to navigate efficiently through space. Every successful slingshot is a testament to our understanding of orbital mechanics and gravity's reliable mathematical nature. Gravity determines how high you can jump. When you jump, you're briefly overcoming gravity, pushing yourself upward with enough force to leave the ground. But gravity immediately begins pulling you back down. The height you reach depends on how much energy your legs put into the jump and how strong gravity is where you're standing. On Earth, an average person might jump a foot or two off the ground. On the Moon, with gravity only 1/6 as strong, the same jump would carry you 6 times higher. You'd rise slowly and fall slowly, hanging in the air for what feels like an eternity. On Jupiter, with gravity more than twice Earth's, jumping would be exhausting and you'd barely clear the ground. Gravity sets the rules for how high birds can fly, how tall trees can grow, and how much weight buildings can support. It determines the maximum height of mountains, the size of planets, and the speed needed to reach orbit. Every physical structure, every living thing exists within limits set by gravitational strength. Jump as high as you want, but gravity always brings you back down, patient and inevitable. Gravity is why the universe has a horizon. Look far enough in any direction, and you reach a limit beyond which you cannot see. This isn't because space ends, but because light from farther away hasn't had time to reach us yet. The universe is about 13.8 billion years old, so light from objects more than 13.8 billion light years away hasn't arrived. This distance defines the observable universe, a sphere centered on us, beyond which lies the unknown. But there's another horizon related to gravity. As the universe expands, distant galaxies move away from us. The farther away they are, the faster they recede. Beyond a certain distance, they move away faster than light can travel toward us. Light from these galaxies will never reach us, no matter how long we wait. This creates a cosmic event horizon, similar in principle to a black hole's, beyond which information cannot pass. Gravity influences this expansion. The distribution of matter throughout the universe creates gravitational fields that slow the expansion locally while allowing it to continue on larger scales. Dark energy, a mysterious force, accelerates the expansion, pushing distant galaxies away faster over time. The interplay between gravity and dark energy determines the ultimate fate of the cosmos and the size of the observable universe. We live inside a bubble of visibility, surrounded by horizons. Beyond them, the universe continues, perhaps forever, filled with galaxies and stars we will never see. Gravity and the expansion of space together define the boundaries of what we can know, creating a universe that is larger than we can ever observe. Gravity affects the color of light. Light climbing out of a gravitational well loses energy. As photons struggle upward against gravity's pull, they stretch to longer wavelengths. This is called gravitational redshift. Light emitted from the surface of a massive star appears slightly redder by the time it reaches distant observers. The stronger the gravity, the greater the shift. Near a black hole, the effect becomes extreme. Light emitted just outside the event horizon is redshifted so much that it fades into the infrared and beyond, becoming invisible. An outside observer watching someone fall toward a black hole would see them grow dimmer and redder, their light stretched and weakened by the immense gravitational field. the reverse happens too. Light falling into a gravitational well gains energy and shifts to shorter, bluer wavelengths. This gravitational blue shift is the mirror image of redshift. Both effects are predictions of general relativity, confirmed by precise measurements. Atomic clocks at different altitudes tick at different rates, and light exchange between them shows measurable shifts in frequency. Gravity doesn't just bend the path of light. It changes the light itself, stretching or compressing its waves depending on whether it's climbing out of or falling into a gravitational field. Every photon carries information about the gravity it encountered on its journey, a subtle signature written into its wavelength. Gravity makes the universe dynamic, not static. Before the 20th century, many believed the universe was eternal and unchanging. Then Edwin Hubble observed that distant galaxies are moving away from us. The universe is expanding. This discovery transformed our understanding. The cosmos isn't frozen in place but evolving, growing larger as time passes. Gravity plays a central role in this expansion. In the moments after the Big Bang, the universe was dense and hot. Gravity pulled everything together, trying to halt or reverse the expansion. For a time, the outcome was uncertain. Would gravity win, causing everything to collapse back into a single point? Or would the expansion continue forever, spreading matter thinner and thinner? The answer depends on the balance between the expansion's momentum and gravity's pull. Observations suggest the universe will expand forever, driven by dark energy that accelerates the expansion. Gravity slows this process locally, binding galaxies and clusters together, but on the largest scales, expansion wins. This means the universe has a history and a future. It began, it evolves, and it will continue changing for trillions of years. Gravity shapes that evolution, clustering matter, forming structures, and resisting the expansion even as dark energy pushes everything apart. The cosmos is not a static backdrop, but a living, changing entity, and gravity is one of the forces writing its story. Gravity connects you to ancient history. The atoms in your body, the ground beneath you, the air you breathe, all of it has a history stretching back billions of years. Gravity played a role at every step. It collapsed the clouds that formed the first stars. It held those stars together while they forged heavy elements. It triggered the supernovae that scattered those elements into space. It gathered the debris into new clouds, new stars, new planets. Earth formed from this recycled material 4.5 billion years ago. Gravity pulled together dust and rock, building a planet layer by layer. It compressed the interior until heat melted rock, allowing heavier elements like iron to sink toward the core. It held the atmosphere in place, creating conditions where water could exist as a liquid. Life emerged in that water and over billions of years evolved into countless forms. Every breath you take contains oxygen produced by ancient photosynthetic organisms. Every bite of food contains carbon that once drifted through interstellar space. Gravity brought it all together, creating the stage where life could appear and flourish. When you rest, when you feel gravity's gentle pull, you're feeling the same force that shaped the universe's history. It's the thread connecting you to stars that died before the sun was born, to clouds of gas that drifted through the galaxy billions of years ago, to the very beginning of time itself. You are part of an ancient story, held together by gravity, shaped by its patient, persistent pull. And now, as you lie here, gravity holds you softly. It presses you into the bed, into the earth, into the universe itself. There's no need to resist. Let it support you. Let it cradle you. You're exactly where you belong, held by the same force that holds galaxies, stars, and worlds. Gravity has been here since the beginning, and it will be here long after, constant and unchanging, the quiet foundation of everything. Rest now. Let gravity do its work. Let the universe hold you as it has always held you, gently, patiently through every moment of your existence. Gravity allows us to measure the universe. Astronomers can't reach out and touch distant stars, yet they know how massive they are, how fast they move, and what they're made of. Gravity provides the tools. When a star orbits another star, the speed and shape of that orbit reveal both masses. When a planet crosses in front of its star, the slight wobble in the star's position tells us the planet's mass. When light bends around a galaxy, the amount of bending maps the distribution of matter, including the dark matter we cannot see. Every measurement relies on gravity's predictable behavior. Kepler's laws, derived centuries ago from observations of planetary motion, still guide spacecraft today. Newton's equations describe how objects fall and orbit. Einstein's corrections account for extreme conditions near black holes and neutron stars. Each layer of understanding builds on the one before, creating a framework that lets us weigh stars, map galaxies, and trace the history of the cosmos. Without gravity's mathematical precision, astronomy would be guesswork. We could see lights in the sky but know nothing about them. Gravity turns those lights into worlds, giving them substance and story. It transforms observation into knowledge, allowing us to reach across billions of light years and understand what we find there. The universe reveals itself through gravity's language, written in orbits and curves, waiting patiently for us to learn how to read it. Gravity shapes sound waves in the atmosphere. When you hear thunder rumble across the sky, you're listening to sound waves traveling through air. These waves move because air molecules bump into each other, passing energy along. But gravity plays a hidden role. It holds the atmosphere close to Earth, creating the medium through which sound travels. Without gravity, there would be no air, and sound would have nowhere to go. Gravity also affects how sound behaves. Air pressure decreases with altitude because there's less weight pressing down from above. This changes the speed of sound slightly at different heights. On mountaintops, where the air is thin, sound travels a bit slower. In valleys, it moves faster. The differences are small, but they're real, another subtle way gravity shapes the world. Even underwater, gravity matters. It creates pressure gradients in the ocean, affecting how sound propagates through water. Whales and dolphins use these properties to communicate across vast distances. Their calls traveling along channels where temperature and pressure guide the sound. Gravity didn't just create the stage for life, it tuned the acoustics, allowing creatures to find each other in darkness, to warn of danger, to sing across miles of empty ocean. Gravity explains why bubbles rise. Drop an ice cube into water and it floats. Blow a bubble underwater and it rises toward the surface. Both happen because of gravity, though it might seem backward at first. Gravity pulls on everything, but it pulls harder on denser materials. Water is denser than ice, so gravity pulls the water downward more strongly and the ice gets pushed up out of the way. The same principle applies to bubbles. Air is less dense than water, so the surrounding water sinks while the bubble rises. This buoyancy is why boats float and why helium balloons drift upward through air. Gravity creates a hierarchy of density. Heavy things sink, light things rise. The ocean separates into layers with cold, dense water at the bottom and warm, light water at the top. The atmosphere does the same, with heavy gases like carbon dioxide settling lower while lighter ones like helium escape into space. Every time you see something float, you're watching gravity at work, sorting matter by density, organizing the world into layers. It's not magic or mystery. It's simply that gravity pulls more strongly on some things than others, and that difference in pull creates motion. Bubbles rise because water falls. Ice floats because water sinks. Gravity gives weight to everything, and in doing so, it decides what rises and what falls. Gravity makes planets round, but asteroids lumpy. If you could visit a small asteroid, you'd find a world of jagged cliffs, sharp edges, and irregular shapes. Some look like potatoes. Others resemble peanuts or dog's bones. They're too small for gravity to reshape them. The rock's internal strength resists gravity's inward pull, and the result is a lumpy, uneven surface. But grow that asteroid larger, add more mass, and eventually gravity wins. Once an object reaches a few hundred miles across, its own weight becomes strong enough to crush rock and flow it like a very slow liquid. High points collapse, low points fill in. Over millions of years, the surface smooths into a sphere. This threshold marks the transition from asteroid to dwarf planet, from irregular chunk to round world. Gravity doesn't care about surface details. It doesn't see mountains or valleys. It only feels mass and pulls it inward equally from all directions. A sphere is the natural result, the shape where every point on the surface is the same distance from the center. It's the most efficient way to distribute mass under its own weight. Every planet, every large moon, every massive object in the universe eventually succumbs to this shape. Gravity erases the roughness, smoothing everything into gentle curves. Gravity makes clocks run at different speeds in orbit. A satellite circling Earth high above the surface experiences weaker gravity than a clock on the ground. According to relativity, this means time flows faster for the satellite. But the satellite is also moving quickly, and motion slows time down. These two effects work in opposite directions. For GPS satellites, the weaker gravity makes their clocks run faster by about 45 microseconds per day, while their motion slows them by about 7 microseconds per day. The net result is that the satellite clocks run about 38 microseconds faster each day than clocks on Earth. This might sound tiny, but GPS relies on incredibly precise timing. Light travels about 1 foot per nanosecond, so even a microsecond error translates to hundreds of feet of position error. Without correcting for both gravitational and velocity time dilation, GPS would drift off course by miles within a single day. Engineers must account for relativity in the system's design, adjusting the satellite clocks before launch so they tick at the right rate once in orbit. It's a practical reminder that relativity isn't just abstract theory. It's woven into the technology you use every day. Your phone knows where you are because engineers understand how gravity affects time. Every turn-by-turn direction, every mapped location depends on corrections for the way gravity warps the flow of seconds and minutes. Time isn't absolute. It bends and stretches, and we've learned to measure those changes with extraordinary precision. Gravity holds neutron stars together against incredible pressure. Inside a neutron star, matter exists in a state found nowhere else in the universe. Protons and electrons have been crushed together into neutrons, packed so tightly that a sugar cube of the material would weigh as much as a mountain. The pressure is unimaginable, far beyond anything achievable in laboratories. Yet the star doesn't explode. Gravity holds it together. The balance is delicate. If gravity were slightly weaker, the pressure would blow the star apart. If gravity were slightly stronger, the star would collapse into a black hole. Neutron stars exist right at the edge, held in equilibrium by forces we still don't fully understand. The outer layers are solid, a crust of iron nuclei arranged in a crystalline lattice. Deeper down, neutrons flow as a superfluid, moving without friction in ways that defy ordinary physics. Some neutron stars spin hundreds of times per second, their surfaces moving at a significant fraction of light speed. The centrifugal force tries to tear them apart, but gravity holds them together. They emit beams of radiation from their magnetic poles, sweeping across space like cosmic lighthouses. When those beams point toward Earth, we see them as pulsars, flashing with clockwork precision. Each flash is a reminder that gravity can contain forces powerful enough to reshape matter itself, holding stars together even when physics pushes them to the breaking point. Gravity affects how fast rivers flow. Water flows downhill because gravity pulls it toward the center of the Earth. The steeper the slope, the faster the water moves. On gentle plains, rivers meander slowly, carving wide curves through the landscape. In mountains, they rush downward in rapids and waterfalls, cutting deep gorges through solid rock. Every river's speed is a conversation between gravity and the terrain. But gravity does more than just pull water downward. It also determines how much erosion occurs. Fast-moving water carries sediment, grinding away at riverbeds and banks. Over millions of years, rivers carve canyons, reshape valleys, and carry mountains grain by grain to the sea. The Grand Canyon exists because the Colorado River, pulled by gravity, spent millions of years cutting through layers of rock. Even the ocean's currents are shaped by gravity. Differences in water density, caused by temperature and salinity variations, create pressure differences that drive vast flows of water around the globe. Warm water rises and spreads toward the poles. Cold water sinks and flows toward the equator. These currents regulate Earth's climate, distributing heat and nutrients, all of it driven by gravity's patient sorting of heavy and light, warm and cold, pulling water into motion that never stops. Gravity makes some moons volcanically active. Most moons are cold, dead worlds, their interiors long since frozen solid. But a few remain geologically active, and gravity is the reason. Jupiter's moon, Io, is the most volcanically active body in the solar system, its surface constantly resurfacing with fresh lava. This activity comes from tidal heating. As Io orbits Jupiter, the giant planet's gravity flexes the moon, squeezing and stretching it. This constant deformation generates heat through friction, melting rock deep inside. Saturn's moon Enceladus experiences similar heating. Though much smaller than Io, it has geysers that spray water ice into space, feeding Saturn's faint outer ring. The source is an underground ocean, kept liquid by tidal heating from Saturn's gravity. These geysers carry organic molecules and salts, suggesting the ocean might have conditions suitable for life. Even Earth's moon once had volcanic activity, billions of years ago when its interior was still warm. The dark patches visible on the lunar surface are ancient lava flows, now frozen and silent. Tidal heating from Earth may have contributed to keeping the moon's interior molten longer than it would have stayed on its own. Gravity doesn't just hold moons in orbit, it needs them, generating heat, driving geology and creating environments where liquid water can exist far from the sun's warmth. Gravity determines how fast planets spin. When a planet forms, the countless collisions that build it up also impart angular momentum. The direction and speed of each impact add together, creating a net rotation. Gravity doesn't determine the rotation directly, but it does influence how that rotation evolves over time. Tidal forces from nearby moons or stars can slow a planet's spin, transferring angular momentum into orbital motion. Earth's day is gradually getting longer. Billions of years ago, a day might have been only 6 hours long. The moon's gravity creates tidal bulges in Earth's oceans and even in the solid crust. As Earth rotates, these bulges don't align perfectly with the moon. The offset creates friction, slowing Earth's rotation and pushing the moon into a slightly higher orbit. The process is slow, adding about 2 milliseconds to the day every century, but over geological time, it's significant. Some planets spin much faster. Jupiter's day is less than 10 hours despite its enormous size. Other planets, like Venus, rotate incredibly slowly and even backward compared to most others. Each planet's spin is a record of its formation, a fossil of ancient collisions preserved in motion. Gravity shapes that motion over time, gradually slowing spins, locking moons into synchronous rotation, and creating the rhythms we observe today. Gravity bends space-time even in empty space. You might imagine that far from any star or planet, space is perfectly flat and empty. But this isn't quite true. Even in the depths of intergalactic voids, the faint gravity of distant galaxies creates gentle curves in space-time. These curves are incredibly subtle, but they're there. Space is never perfectly flat anywhere in the universe. These gentle warps guide the paths of light and matter, even across vast distances. A photon traveling through seemingly empty space still follows curves created by matter billions of light years away. The path might deviate by only a tiny fraction, but the cumulative effect over cosmic distances can be significant. Gravitational lensing maps these curves, revealing the invisible scaffolding of space-time itself. This means the universe has a shape, a geometry determined by the total mass and energy it contains. Current observations suggest the universe is very close to flat on the largest scales, but not perfectly so. Gravity's influence extends everywhere, creating a landscape of gentle hills and valleys in space-time, invisible to the eye but detectable through the motion of light and matter. Even in the emptiest regions, gravity's signature remains, a faint whisper of distant mass shaping the fabric of reality. Gravity makes walking possible. Every step you take is a negotiation with gravity. You lean forward, shifting your weight. Gravity pulls you down, but you catch yourself by moving your foot forward. This controlled fall is what walking is. Without gravity, there would be nothing to fall toward, and walking as you know it would be impossible. Astronauts on the moon had to relearn how to move. With only 1/6 of Earth's gravity, each step sent them higher and farther than intended. They bounced rather than walked, developing a loping gait that looked strange but was efficient in the low gravity. On the space station, with no gravity at all, astronauts don't walk. They push off walls and float, drifting through the modules like swimmers in invisible water. Gravity also determines how much energy walking requires. On Earth, your muscles work against gravity with every step, lifting your body weight repeatedly. On a lighter world, walking would be easier. On a heavier one, exhausting. the strength of your bones, the power of your muscles, even the rhythm of your gait, all evolved under Earth's specific gravitational pull. You are adapted to this exact force, shaped by billions of years of life, learning to move through this particular strength of pull. Every step is a testament to that long history. Gravity creates equilibrium in the universe. The cosmos is full of opposing forces. Expansion pushes galaxies apart. Gravity pulls them together. Stars generate outward pressure from fusion. Gravity compresses them inward. Planets try to tear themselves apart from rotation. Gravity holds them together. At every scale, gravity provides the counterbalance, the force that resists change and creates stability. This balance allows structures to persist. Without gravity, stars would explode in the instant fusion ignited. Planets would fly apart. Galaxies would dissolve into scattered stars drifting through infinite space. The universe would be formless, a thin gas spreading forever without pattern or purpose. Gravity prevents this, creating pockets of order in the expanding cosmos. Even the expansion itself may eventually be balanced by gravity. If there's enough matter in the universe, gravity could one day halt the expansion and reverse it, pulling everything back together in a big crunch. Current evidence suggests this won't happen, that dark energy will win and the expansion will continue forever. But the fact that it's even a question shows gravity's power. It's the only force capable of resisting the universe's expansion, the only thing that could bring everything back together. In the endless push and pull of cosmic forces, gravity is the anchor, the weight that keeps everything from flying apart into meaningless chaos. And in this moment, as you rest, you feel that anchor. Gravity holds you, it connects you to the earth, to the sun, to the galaxy, to everything. You're not separate from the universe. You're part of it, held in place by the same force that holds stars and planets. There's comfort in that connection, a sense of belonging that goes deeper than words. You're exactly where you should be, supported by the cosmos itself. Let that feeling settle over you. Let gravity do what it has always done. Let it hold you gently as you drift toward sleep, knowing that this force has been here since the beginning and will be here long after. Constant and unchanging, the quiet foundation beneath everything. Rest now, the universe has you. You're safe, held, and home. Gravity shapes the way clouds form and drift. High above, water vapor rises on warm air currents, climbing until it reaches altitudes where temperature drops and pressure decreases. There, the vapor condenses into tiny droplets, gathering into the white masses we call clouds. But gravity never stops pulling. Each droplet is drawn downward, and only the upward push of warm air keeps them suspended. When droplets grow heavy enough, merging with others until they can no longer be held aloft, they fall as rain. Different clouds form at different heights, sorted by the balance between rising air and gravity's downward tug. High cirrus clouds, made of ice crystals, drift in the thin upper atmosphere. Lower cumulus clouds, thick and puffy, ride warmer air closer to the ground. Gravity determines where each type can exist, creating layers in the sky as distinct as layers in the ocean. Even fog is simply a cloud that has settled to the surface, its droplets too heavy to rise but too light to fall as rain. Storm clouds grow tall when powerful updrafts overcome gravity's pull, carrying water droplets high into freezing air. There they become hail, ice pellets that fall and rise repeatedly, growing larger with each cycle. Eventually, they become too heavy even for the storm's fury to hold, and they plummet to earth. Every raindrop, every snowflake, every piece of hail is gravity's work, pulling water from sky to ground in an endless cycle that has continued for billions of years. Gravity guides how plants grow toward light. A seed buried in soil somehow knows which way is up. Roots grow downward, following gravity's pull toward water and nutrients deep in the earth. Stems grow upward, defying that same pull to reach sunlight above. This response to gravity is called gravitropism, and it's essential for plant survival. Without it, roots might grow toward the surface and wither, while stems might burrow deeper into darkness. Tiny crystals inside plant cells settle under gravity's influence, telling the plant which direction is down. When the plant detects it's tilted, cells on one side grow faster than the other, bending the stem or root back toward the correct orientation. This process continues throughout the plant's life, constantly adjusting growth to maintain proper positioning. Even a plant growing on a hillside will adjust, its stem curving to grow vertically despite the slanted ground. In space, without gravity's guidance, plants grow in confused tangles. Roots spread in all directions, stems curl randomly, and the plant wastes energy growing in patterns that would never work on Earth. Experiments aboard space stations show that plants can survive without gravity, but they struggle. They evolved over billions of years with gravity as a constant guide, and removing that guide reveals how deeply it's woven into their biology. Every flower reaching toward the sun, every root digging through soil, is following instructions written by gravity into the code of life itself. Gravity affects how your heart pumps blood. Stand up quickly, and you might feel dizzy as blood drains from your head, pulled downward by gravity. Your heart must work harder to push blood upward against this pull, maintaining pressure throughout your body. Blood vessels in your legs constrict to prevent pooling. Your heart rate increases slightly. These adjustments happen automatically, your body compensating for gravity without conscious thought. Astronauts in space face the opposite problem. Without gravity pulling blood downward, it redistributes toward the head and chest. Faces become puffy, legs thin out. The heart doesn't need to work as hard, and over time it actually shrinks slightly, becoming less muscular. When astronauts return to Earth, they must readjust. Some feel faint when standing as their cardiovascular system relearns how to fight gravity. Lying down removes most of gravity's effect on blood flow. Your heart can rest, pumping with less effort because it no longer has to overcome the vertical distance between head and feet. This is part of why sleep is so restorative. Your cardiovascular system gets a break from the constant work of defying gravity. Every heartbeat you feel right now is slightly easier than when you were standing, your body taking advantage of this horizontal position to rest and repair. Gravity determines the maximum height of trees. Water must travel from roots to leaves, climbing through the tree against gravity's pull. This journey requires energy, and the taller the tree, the harder the journey becomes. Capillary action helps, as does the evaporation of water from leaves, creating suction that pulls more water upward. But there are limits. Eventually, gravity makes the journey too difficult and water can't reach the top. The tallest trees on Earth, coast redwoods, reach heights around 380 feet. This seems to be close to the maximum possible. Taller trees would struggle to transport water efficiently. Their uppermost branches would suffer from water stress, unable to photosynthesize effectively. The tree would waste resources supporting a top section that contributes little to its survival. Gravity sets this boundary, creating a ceiling beyond which trees cannot grow. On a planet with weaker gravity, trees might grow taller. On one with stronger gravity, they'd be shorter and sturdier. The shape of forests, the height of canopies, the entire structure of terrestrial ecosystems is constrained by gravitational strength. Every tree reaching toward the sky is pushing against this limit, growing as tall as gravity will allow. The forests around you exist in the form they do because gravity shaped them, just as it shaped mountains and rivers and every other feature of the landscape. Gravity makes sand dunes migrate across deserts. Wind lifts grains of sand and carries them short distances before gravity pulls them back down. They bounce and skip across the surface, never rising far. When wind encounters a dune, it sweeps sand up the gentle slope on the windward side. At the crest, the wind slows and gravity takes over. Sand grains tumble down the steep slip face on the opposite side, accumulating there. Over time, this process moves the entire dune. Sand is constantly removed from one side and deposited on the other. The dune migrates downwind, sometimes traveling hundreds of feet per year. Ancient dunes can be found far from modern deserts, fossilized in sandstone, marking places where deserts existed millions of years ago. Gravity was there too, pulling sand into the same patterns it creates today. Some dunes grow tall, others spread wide. The shapes depend on wind patterns, sand supply, and vegetation. But gravity influences every form. It determines the steepest angle sand can pile before sliding, called the angle of repose. It pulls sand downward after each gust of wind. It sorts grains by size, with heavier particles settling closer to the source while lighter ones travel farther. Deserts are shaped by wind, but gravity writes the rules wind must follow. Gravity affects how insects walk on water. Small creatures like water striders can stand on the surface of a pond, their weight distributed across multiple legs. They don't break through because surface tension holds the water molecules together, creating a flexible skin. But gravity is still pulling on them, trying to drag them down. The insect's low weight and the water's surface tension reach a balance, allowing the insect to stand where heavier animals would sink. If gravity were stronger, surface tension wouldn't be enough. The insect would break through and plunge into the water. If gravity were weaker, even larger creatures might walk on water, their weight insufficient to overcome surface tension. The boundary between floating and sinking is determined by the ratio of weight to surface area, and gravity defines weight. Every water strider skating across a pond is balanced on this edge, held up by molecular forces that barely overcome gravity's pull. Larger insects can't perform this trick. Their weight increases faster than their surface area as they grow, and eventually gravity wins. They're too heavy for surface tension to support. This sets a size limit on water-walking creatures, another example of gravity constraining what's possible in nature. The smallest details of life, down to which insects can walk on water, are governed by gravity's quiet mathematics. Gravity causes glaciers to flow like slow rivers. Ice seems solid and immovable, but under its own weight, it behaves like a thick fluid. The pressure at the bottom of a glacier, created by the weight of all the ice above, makes the ice there slightly plastic. It can deform and flow, creeping downhill at a pace measured in inches per year. Over centuries, glaciers carve valleys, transport boulders, and reshape entire mountain ranges. The flow is uneven, Ice near the surface moves faster than ice at the bottom, which is slowed by friction against bedrock. Crevasses open where the glacier flows over uneven terrain, the ice cracking under stress. Seracs, towering blocks of ice, form where the glacier cascades over cliffs. All of this motion is driven by gravity pulling the ice downslope, patient and relentless. When glaciers reach the sea, chunks break off in a process called calving, creating icebergs. These drift with ocean currents, slowly melting. The ice that breaks free began as snow falling on mountains decades or centuries earlier, compacted into ice, carried by gravity to the sea. Gravity doesn't just pull objects downward, it can move entire mountains of ice, grinding stone, shaping landscapes, creating features that last millions of years after the ice has melted away. Gravity influences how rainbows appear in the sky. After a rainstorm, countless water droplets remain suspended in the air, falling slowly under gravity's influence. Sunlight enters these droplets, bends as it passes through, reflects off the back surface, and exits at an angle. Different colors of light bend by different amounts, separating into the spectrum you see as a rainbow. The arc's position depends on the angle between the sun, the droplets, and your eyes. Gravity determines where the droplets are and how fast they fall. If they fell faster, they'd pass through the light more quickly and the rainbow would shimmer and fade. If they hung motionless, the colors might blur together. The gentle fall creates stability, holding droplets in place long enough for the light show to develop. Every rainbow you've seen was painted by sunlight, but positioned by gravity. Double rainbows occur when light reflects twice inside the droplets before exiting. The second arc appears fainter and with colors reversed. Sometimes even a third or fourth rainbow is visible under perfect conditions. Each one depends on droplets falling at just the right speed, suspended in air by the balance between gravity and air resistance. The beauty of a rainbow is temporary, lasting only as long as droplets remain aloft. When they fall too far or evaporate, the colors vanish, leaving only memory. And so we come to the end of our journey through gravity's gentle mysteries. From the smallest raindrop to the largest galaxy, this invisible force has guided us through a universe more strange and beautiful than we often pause to consider. Gravity is always there, patient and constant, holding everything together with a pull so soft we barely notice it, yet strong enough to shape the cosmos itself. As you rest now, feel that same force cradling you, connecting you to stars and planets across unimaginable distances. You are held by the universe, part of something vast and ancient. Let that thought carry you softly into sleep, knowing you are exactly where you belong.